Hello, everyone. Today I will introduce our ECIR 2021 paper, which is a zero-attentive variance matching network for review modeling in a recommendation system. The authors of this paper are Han Shizheng, Zhichao Xu, and Qingyao Ai. So first of all, I will introduce the motivation and what it means to the review-based recommender system. In e-commerce platform, each item will have different reviews left by different users, and each user will also leave different reviews on different items. This review can offer very valuable information on predict the user's preference and the item's properties. So in our work, we will first investigate the pros and cons of the previous review-based recommender system. And based on our findings, we will propose a new model to solve the issue in previous works. So roughly, the neural network-based review-based recommender system can be review-based recommender systems can be divided into two parts. The first part is called the Siamese network, and the second part is called the interaction-based network. So in Siamese network, we will use two parallel networks to encode the user's preference from their reviews and form the corresponding user rotation, and use the other item network to extract the reviews from the camera to form the corresponding item rotation. And after we have the user and item rotation learning from the user and item review corpus, we can put them into some prediction layer to output the final rating prediction. And for the interaction-based network, the user orientation are learned not only from the user reviews, but also from the target item reviews. And similarly, the item rotation is not only learned from the reviews of list items, but also depending on the reviews that the reviews that left by the current user. And so after we learn the dynamic user orientations and dynamic item orientation, we can similarly to take them as input to some prediction layer and output the rating prediction. So the intuition behind this interaction-based network is that different reviews, target items, different user history items he built before might play different roles in determining his preference to the target item, hence lead to dynamic user representations. So the advantage of the Siamese network is that it's very easy to implement and very simple. But the disadvantage of that is very obvious, is that because it can only learn the static user orientation or static item orientation, this model cannot capture the user's dynamic purchasing behavior. So I will illustrate you this argument by this example. So from this figure, we can find no matter what the target item is, whether it's the white sneaker or whether it's the white camera, the user's representation to these corresponding items are always the same, which is a static vector. However, if we see the figure more carefully, we can find actually the users bought a similar black sneaker before, so the review he leaves to this black sneaker might play a more important role when we want to predict the user preference to this target item, which is a white sneaker. And also, if the target item is a white camera, then the user's review leads to this black camera in his history purchasing transaction might be more important to form the dynamic user representation in this session. So based on this finding, in our community, people develop the interaction-based network to try to capture the user's dynamic purchasing behavior, as we mentioned before. However, when we do the experiment to compare the performance between the Siamese networks and the interaction-based network, we surprisingly finding that the Siamese network can consistently outperform the interaction-based networks across 4 different data sets. And the metric we use in this table is the mean square error. So the lower value is the better the performance is. So from this table, we can find the mean square error of this Siamese network is consistently lower than the mean square error of the interaction-based network in 4 different data sets. So this finding leads us to two very research questions. First of all, is that why the interaction-based network fail, even though their models more complex and seems more promising because they can fit the user's dynamic purchasing behavior. And the second is that can we modify the network if we can find the reason behind the failure of this interaction-based network? So let's first focus on the first point. So in the next few slides, I will use our first version of the model to illustrate what's the basic component of the interaction-based network, because the high-level idea of these interaction-based networks are very similar to each other. So firstly, we will compute each item's relevance matching score to the target item by computing their review similarity. So technical speaking, we will use each item's review as a query, and all reviews written to this target item as a document. So this program can be transformed to determine the relevance level between the item's query to the target item's documents by putting these two text sources into the relevance matching layer. And the output of this relevance matching layer will be the relevance matching score. So after we compute the relevance matching score for each items, we will normalize this relevance matching score into the relevance matching weights. And in this example, we can find because this user buy the similar item, which is a black sneaker before, so the relevance matching weights for this black sneaker might be have the higher value. And also, we'll use the review encoder in our example, in our model. This review encoder is a transformer to encode each item's review into a single vector to represent the user's preference or opinion on the corresponding item he bought before. So after we have the vectors and the corresponding relevance matching weights to the target item, we can apply the weighted sum of these vectors to form the final user's dynamic representation. Because we can find these relevance matching weights, these vectors have very high relevance matching weights, so the dynamic user orientation in this session will heavily depend on this vector, which is a representation of the review of these black sneakers when the target item is the white sneaker. And similarly, if the target item is a white camera, then the relevance matching weights for this white camera will be very high. So the final dynamic user orientation will heavily depend on the vectors that represent the user's opinion on the black camera he bought before when the target item is the white camera. However, in this scenario, this first version of our model cannot handle very well. I will argue that this scenario might be the main reason that most of the interaction-based network might fail. So let's see more carefully. So when the target item is pretty new that this user never seen before, like in this case, it's the hair dryer that the user have no clue when he searched for his past reviews. So in this case, the user should pay attention to none, right? Because he have no any idea on this hair dryer. So if the users paid attention to none, he should have the dynamic, he should have a zero vector to represent his current dynamic orientation. Because the zero vector doesn't have contain any noisy information. However, if we follow the same procedure as we done before, to first compute the random matching scores for each of the item to a target item, our model is well trained that can successfully identify that all of these items are irrelevant to the target item and output a very large negative rarest matching scores. In our case, for simplicity, let's just assume all of these scores are negative 5.0. And then we normalize these scores into the rarest matching ways, and each way in this case is 0.33. And we apply the weights into this iteration component. And to form the final user dynamic orientation, we can find, because of all the weight, it's 0.33. So the final dynamic user orientation will be just the average embeddings of all of these vectors that from the user history item. So because this is average embedding, so the final dynamic user orientation are definitely not a zero vector. So it contains a lot of noisy information, which is contradictory to our expectation. In our expectation, we want this dynamic orientation is a zero vector where the target item is totally new to the user. So we argue that the reason behind the failure of the previous iteration-based networks are in 2 points. The first point is that the existing models are ignore the fact that the current target item is very likely beyond the scope of the items that the user bought before. In our statistics, this phenomenon accounts for 40% to 60% of used item pairs on different data sets in our experiment. And since this phenomenon is ignored by previous work, so these interaction-based models will handle this situation and will lead to some bug and contributes to the performance degrade. So after we find a reason, the second research question is that can we modify the networks based on our findings? So first of all, I will introduce 2 principles that I think to train a good interaction-based network to capture the user's dynamic purchasing behavior. The first principle is that if the target item is relevant to any of the user history items he bought before, then the corresponding relevant item should contribute more on the final user dynamic orientation. But the second principle, it's equivalently important, is that if the target item is irrelevant to all of the user history item he bought before, then the user dynamic orientation is better to be a zero vector that contains no information, which is ignored by previous interaction-based models. So to satisfy the 2 principles, we add a zero attention component. So the first thing in this component is a static zero score, which will be appended at the end of the relevant matching scores vector. So let's reply our previous failure example again. So because all of these items are irrelevant to a target item, so the relevant matching score for these items will be negative 5.0, as we mentioned before, with this static zero score. And after that, we normalize these relevant matching scores into the rarest matching ways and we will find that the weight for this zero score will be a very high probability. So it leads to the final dynamic user orientation highly dependent on this zero vector because it has a very high weight. So because this is a zero vector, so the dynamic user orientations will be a vector which is very close to a zero vector when the target item is irrelevant to previous items that usable before. And also, if the target item is actually relevant to user's history item, so for example, in this case, the user bought the black sneaker before, then this black sneakers relevant weights will still be very high even with at least static zero score. So the final dynamic user orientation will still depend on the representation of the black sneaker the user bought before when the target item is the white sneaker. So we can see all these two principles are satisfied after we add the component of the zero attention, right? So this is a whole architecture of our model. We'll use the interaction-based component to form item-dependent user orientation. And also we'll get the item-independent user orientation. And also we will get the user-independent item orientation. And to form the final user orientation, we will combine the item-independent and item-dependent user orientation by taking it as an input to some feature transformation layer, and so is the item representation. And after that, list representation will go through a prediction layer to output the final rating. Also, to better train our Relevance matching module, we'll use the ground truth review to the target item to better train our Relevance, to better align the ground truth review and target item document by using the auxiliary task. So in our experiment, we first compare the result between our model with different types of model, like the non-text-based model and the Siamese review-based model and the iteration-based review-based model across two different Amazon datasets by using the mean square error as the metric. And from this table, we can find our model can considerably outperform all of the other models in 4 different datasets. So in our first case study, we randomly sample 40 user item pair, and for each UI pair, we will keep at most 11 reviews written from user, and also add a slot for a zero static score. So in each slot, we'll compute the relevant matching weights between each user review to the target item to form this heat map. So in this heat map, we can figure out that there are roughly 50% of the user item pair have a very high relevant matching weights for this zero static score. So that means in this pair, we cannot find any relevant review from user to the target item. However, there are other interesting parts like for the item 4 and the target item 5, we can find the review 6 from the user review that have very high relevance score to the target item. The second case study is that we investigate the distribution of the user item pairs with different number of relevant reviews. We set a threshold when alpha k larger than 0. So we will find across 4 different data sets, there are roughly 45% to 60% of the UI pair doesn't have any relevant reviews. However, the interesting part is that in some cases we may can find reviews that have number larger than 3 when the user have the relevant reviews to a target item. So in our final case study, we randomly sample two user item pair and two user item pair. And in this user item pair, we can find a very high relevant review of the user to a target item. So we show the text of this high relevant user review and some snip of the target item document. So let's see the first example. In this target item document, we can find some keywords to illustrate the description of this item. Like this item is a Gyro Hercules helicopter, and he has a property that he can keep on going and not falls down, which means that this helicopter are very robust to the dynamic environment. And similarly, the high revenue review we find is also describe the user's previous purchasing experience on the Gyro Hercules helicopter. Also, he really appreciate these helicopters have the properties that can truly withstand a hard fall, which means that it's also strong to the dynamic environment. And the second experiment is in the second experiment, we can find a target item. It's our artificial craft. It's very suitable. It's a very suitable present for the Christmas vacation for the 3-year-old children. And in the higher review, we find the user also mentioned that she has a granddaughter, my and which is and his daughter is 3 year old, and he gave away some art projects for his uh, granddaughter in Christmas before. Yeah, this is a whole description. Yeah, thank you so much.